Hi everyone, today we're going to be talking about Maxwell Boltzmann's distribution curves. So firstly, we're going to do a quick recap of activation energy. Activation energy is the minimum amount of energy required by reactant particles to form product particles. What this means is that activation energy is the minimum amount of energy that must be available to reactants for a chemical reaction to actually occur. And if you think about the collision theory, the activation energy is the amount of energy that is needed for successful collisions. And next, we're going to talk about transition state. So transition state is the state corresponding to the highest potential energy along the reaction coordinate. And if we look closer at this, a transition state is a species that forms when a reaction has the activation energy needed to break the bonds in the reactants. The transition state is formed midway between the reactants and the products, with partially broken and partially formed bonds. This makes the transition state unstable, and it quickly rearranges itself to form the products. We'll go into more depth about this when we start talking about mechanics, but for now, just know that it's the state corresponding to the highest potential energy along the reaction coordinate. If we take a look at this energy profile diagram over here for this exothermic reaction, we can see that the reactants have more energy than the products. And this is due to the loss in energy during the chemical reaction, making it the exothermic reaction, which is also supported by the fact that the enthalpy change here is negative. And if we go back to activation energy and transition state, you can see that the activation energy is shown here in green, and we can see that the transition state is where the highest potential energy occurs in this reaction coordinate, which is right here. And this little hump here shows the activation energy, as the reactants needed to gain some energy first before it could start the reaction and form the products. If we take a look at this energy profile diagram over here for this endothermic reaction, we can see that the reactants hold less potential energy than the products. And this is due to the fact that endothermic reactions gain energy throughout the reaction. And this is also supported by the positive enthalpy change over here. And the activation energy is shown here with the green once again, and the transition state is also shown. And one extra thing to take note of is that the activation energy always starts from the potential energy of the reactants, which is right here, and goes all the way up to the transition state. Now we'll take a look at the energy profile diagrams for catalyzed reactions and uncatalyzed reactions. If we take a look at this exothermic reaction over here, we can see the original curve that we saw previously, where the reaction occurred without the catalyst. And like mentioned, we have the activation energy here, transition state here, and the enthalpy change, which is negative. But as you can see, with the catalyst, this hump over here is a lot smaller. This means that the amount of energy needed as activation energy is a lot lower. And the reason for this is because catalysts provide the reaction with an alternate pathway for it to follow. That is why this arrow over here is shorter than the one on this side. And this is the same that goes for the endothermic reactions. So as you can see, the endothermic reaction, we have the activation energy without a catalyst, which is in pink, and the activation energy with catalyst, which is in blue. And like mentioned before, the activation energy spans the entire height of the peak and not just the hump over here. And of course, for the one with the catalyst, it's slightly lower, the amount of potential energy and activation energy that is needed. So this overall activation energy is lower. The enthalpy change remains the same regardless if a catalyst was used or not, because like mentioned before, all the catalyst does is provides an alternate pathway for the chemical reaction to follow meaning that it needs a lower activation energy to actually begin. But this doesn't actually change the amount of energy that the products have in the end over here. Now we'll talk about the actual Maxwell Boltzmann's distribution curve. As a quick reminder, temperature is the measure of the average kinetic energy of the molecules. And in a sample of particles at a given temperature, not all of the particles will possess the same amount of energy. Some fraction of the molecules will possess a very high energy, and another will have a very low energy. But most of the particles will have energy that is in between these two extremes. So this is shown through the Maxwell Boltzmann distribution curve. And as you can see, the y-axis of the graph is the number of molecules possessing the given energy, and the x-axis is the amount of energy that these particles or molecules possess. The area underneath the graph is the total number of particles that is present. And since this section of the graph has the largest area, we can say that most particles have moderate energies. And this small section here shows that only a few particles have very low energies. And same goes for this section over here. And we can say that only some particles have very high energies. Now we'll talk about the Maxwell Boltzmann distribution curve and activation energy. Activation energy is shown as a line on the graph. So this line shows the amount of energy that the reactant particles need for a chemical reaction to occur. The number of particles represented by the area under this curve don't have enough energy to react, since they are on the left-hand side of the activation energy. And as a reminder, the x-axis shows the amount of energy that the particles possess. So if it's beneath this activation energy here, it doesn't have enough energy to react. And only the number of particles represented by the area under this part of the graph have high enough energies to react. Since the amount of energy of the particles over here is higher than this line, that means that they have enough energy to react. Moving on, now we'll talk about the effect of temperature and the Maxwell Boltzmann distribution curve. This blue curve over here shows a sample of particles within an environment of 300 Kelvin, and the red one within an environment of 310 Kelvin. The curve for the higher temperature has a lower peak height. As you can see, the blue one's peak is over here, and the red one is over here. However, the red curve no longer has the same shape as the blue curve. And the reason that it was stretched to the right is so that the area beneath the curve remains constant. Because the only thing that we have changed here is the temperature, but the number of particles still remains the same, meaning that the area of these two curves must be the same as well. However, since the graph has been stretched to the right, the particles now possess higher energy. So more particles now have a greater energy than the activation energy as well. The area underneath the blue curve here, that is above the activation energy, is only this much. However, the particles that hold a higher temperature have a larger proportion that is above the activation energy. So essentially what that means is when you have a higher temperature, you would have more particles that have enough energy to react. And now we'll talk about the Maxwell Boltzmann distribution curve and the effect of catalysts. So as a reminder, catalysts alter the activation energy by lowering the activation energy. So how this is shown on the graph is we move the activation energy line further down, so further towards the left. So as you can see, this line over here is the activation energy for the uncatalyzed reaction, and this one over here is the line for the activation energy of the catalyzed reaction. However, since the presence of a catalyst doesn't alter the average kinetic energy of the particles, the shape of the curve remains the same. But By moving this activation energy line to the left slightly, we have increased the proportion of particles with enough energy to react. And we can see this because the area underneath the graph with this line over here is larger than the one with this line over here. And that is about all for Maxwell Boltzmann's distribution curves. I hope you've learned something, and please check out our multiple other videos on IGCSE and IB Sciences. Thank you.